We're counting down the 10 space discoveries that seemed absolutely impossible until scientists proved they were real. From breakthroughs that defy the laws of physics to worlds that should not exist, each item on this list shattered long-held beliefs about the universe. Prepare for a journey through cosmic mysteries and jaw-dropping surprises as we reveal the discoveries that forced scientists to rewrite the rules. Which revelation tops them all? Let's begin, starting with number 10. In 1998, two rival teams of astronomers set out to measure the fate of the universe, using distant Type 1a supernovae as cosmic mileposts. These exploding stars, known for their reliable brightness, allowed researchers to compare apparent and intrinsic luminosity, revealing how fast the universe was stretching. The expectation was simple. Gravity should slow expansion over time, like a ball thrown upwards slowing as it rises. Instead, the data told a different story. Distant supernovae appeared dimmer than predicted, not because they were farther away, but because the universe's expansion was accelerating. Both the High-Z Supernova Search Team and the Supernova Cosmology Project raced to publish their results, confirming each other's findings. This discovery forced scientists to confront the existence of a mysterious force now called dark energy, making up about 68% of everything in the cosmos. No one knows what dark energy actually is, only that it acts like a cosmic anti-gravity, pushing galaxies apart faster and faster. The 2011 Nobel Prize in Physics honored this breakthrough, but the true nature of dark energy remains one of the universe's deepest secrets. In 1992, a faint, rhythmic beacon from deep space caught the attention of astronomer Alexander Wolszczan at the Arecibo Observatory. The source, PSR B1257+12, was a millisecond pulsar, a stellar corpse spinning over 160 times per second, firing radio pulses with clockwork precision. But something was off. The timing of those pulses showed tiny repeating delays, as if the pulsar itself was wobbling. By tracking over 4,000 pulse arrivals, Wolszczan and his colleague Dale Frail uncovered the first confirmed planets beyond our solar system, 2, then 3 rocky worlds, each orbiting just a fraction of the distance between Earth and the Sun. What made this discovery so shocking was the setting. PSRB 1257+12 had survived a supernova, an explosion so violent it should have obliterated any nearby planets. Yet these worlds existed, likely forged from the wreckage itself, a second generation born in a disk of debris circling the neutron star. Their environment is a true cosmic hellscape, relentless radiation, particle storms, and no hope for atmosphere or life. Yet, against all odds, these zombie planets endure, circling the remnants of a dead star in a place where nothing was ever supposed to survive. In 1916, Albert Einstein wrote that space itself could ripple like the surface of a pond, but he doubted anyone would ever detect such faint distortions. The numbers seemed hopeless. A passing gravitational wave would stretch and squeeze 4 kilometers of space by less than 1,000th the width of a single proton. For nearly a century, the idea remained a mathematical curiosity. Then, on September 14, 2015, the impossible became real. 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana, registered a fleeting signal just 7 milliseconds apart. It was the signature of 2 black holes, each about 30 times the mass of the Sun, spiraling together and colliding 1.3 billion light-years away. The instrument that caught it, LIGO, used laser beams bouncing between mirrors in vacuum tunnels 4 kilometers long. Every vibration, every distant truck, even quantum noise, threatened to drown out the signal. Yet the data showed a clear, rising chirp, space-time itself, ringing from the black hole's final dance. For the first time, humanity could listen to the universe's most violent events. Gravitational waves were no longer theory. They had become a new way to explore the cosmos. For decades, the moon was the definition of barren. Every Apollo sample and every early analysis pointed to a surface baked, bone dry from sunlight and stripped by the solar wind. The idea of finding water, real water molecules, seemed about as likely as stumbling on a lake in the Sahara. That belief came crashing down in 2020. NASA's Flying Observatory SOFIA turned its infrared spectrometer toward the sunlit soil of Clavius crater. Instead of the expected silence, the instrument picked up a distinct signature at 6.1 microns, a vibrational fingerprint unique to water molecules, not just hydroxyl or stray hydrogen. The numbers were small but undeniable, between 100 and 400 parts per million, embedded in the uppermost layer of lunar regolith, likely trapped in glass beads or mineral defects. At the same time, the Lunar Reconnaissance Orbiter mapped concentrations of hydrogen in the Moon's permanently shadowed polar craters. These cold traps, untouched by sunlight for billions of years, hold vast reserves, possibly billions of tons, of water ice locked beneath the surface. Unlike the scattered molecules in sunlit soil, this ice could be mined, melted, and turned into drinking water, breathable air, or even rocket fuel. The discovery flipped the script on lunar exploration. What was once a lifeless wasteland is now a target for future missions, not just for science, but for survival. Water on the Moon is not just a curiosity, it is a resource that could support a permanent human presence, turning science fiction into engineering reality. In the early 1960s, astronomers began to notice strange, star-like points of light in the night sky. These objects looked like ordinary stars through a telescope, but their spectra told a different story. Instead of the familiar fingerprints of hydrogen and helium, their light was stretched to such extreme redshifts that, by calculation, they had to be billions of light years away. Yet they shone with the brilliance of more than 100 galaxies combined, all packed into a region no larger than our solar system. The brightest, 3C273, outshone the entire Milky Way by a factor of 1,000, but appeared as a single point even through the world's largest telescopes. The puzzle deepened as astronomers tracked rapid changes in brightness over just days or weeks, far too fast for something the size of a galaxy. No known process, not even nuclear fusion, could explain such concentrated power. The answer, though almost as wild as the mystery, lay at the very heart of these cosmic lighthouses. Deep within each quasar, matter spirals into a supermassive black hole, millions or even billions of times the mass of the Sun. As gas falls inward, it heats up to billions of degrees, releasing energy with an efficiency 10 times greater than fusion. Up to 10% of the infalling mass is converted directly into light. Quasars revealed that supermassive black holes are not rare monsters, but common engines at the centers of young galaxies. Their discovery forced astronomers to rethink what galaxies are and what they become. For the first time, the universe revealed just how much power could be unleashed when gravity and matter collide on a cosmic scale. A single millisecond. That's all the warning the universe gives before unleashing one of its most powerful signals, a fast radio burst, or FRB. These flashes erupt with as much energy as the Sun produces in an entire year, squeezed into a sliver of time shorter than a blink. When astronomers first picked up these signals in 2007, skepticism ruled the day. Some blamed microwave ovens, others blamed stray electronics. But as more telescopes joined the search, CHIME in Canada, ASCAP in Australia, and FAST in China, the pattern became impossible to ignore. FRBs were real, and they were everywhere, arriving from billions of light years away. Each burst is so intense, it can outshine every star in its host galaxy for that instant. The signals sweep across radio frequencies, showing the telltale delay that comes from passing through intergalactic plasma. Their fluence can reach 100 Jansky milliseconds, a number that hints at staggering energy density. Most FRBs never repeat, but a handful fire off multiple times from the same spot, each with its own fingerprint. The leading theory points to magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. In April 2020, the magnetar SGR 1935 plus 2154 in our own galaxy sent out a radio burst matching the profile of distant FRBs, finally linking at least some of these cosmic signals to magnetar flares. These fields are so strong, they can twist atoms into new shapes and unleash bursts that ripple across the universe. Yet with thousands of FRBs catalogued and more discovered every week, the full story remains unsolved. The universe is sending out cosmic Morse code, but the message is still a mystery. Black holes were once thought to be the most silent objects in the universe, places where matter vanished, and nothing, not even light, escaped. Yet, in the late 1990s, astronomers using NASA's Rossi X-ray Timing Explorer discovered something no one expected. Black holes have a heartbeat. In systems like GRS 1915+105, a black hole weighing 14 times the Sun pulses in X-rays 67 times every second. These signals, called quasi-periodic oscillations, are astonishingly regular, like a cosmic heartbeat coming from the edge of oblivion. The source of this heartbeat lies in the accretion disk, a whirling maelstrom of gas spiraling toward the event horizon. Instead of pure chaos, the disk produces pulses with clockwork precision. The frequency of these pulses depends on how close the material orbits to the black hole's edge. Because gravity is so extreme, only matter at the innermost stable orbit can survive more than a few turns before plunging in. The faster the pulses, the closer the disk, revealing both the mass and the spin of the black hole. For GRS 1915+105, the 67 Hz pulse points to a black hole spinning at nearly the maximum rate allowed by physics, about 98% of the speed of light. Quasi-periodic oscillations have become a stethoscope for black holes. By listening to these X-ray beats, astronomers can weigh black holes and measure their spin with a precision once thought impossible. Each pulse is a direct probe of gravity at its most intense, offering a glimpse into the ordered patterns hidden within the universe's most chaotic places. 40 light-years from Earth, in the faint glow of the constellation Aquarius, an ultra-cool dwarf star called TRAPPIST-1 holds a planetary system that rewrote the odds of finding another Earth. In 2017, astronomers using the TRAPPIST and Spitzer telescopes watched the star's light dip in a repeating pattern, 7 distinct planets, each about the size of our own, passing in front of their tiny sun. 3 of these worlds orbit in the habitable zone, where temperatures could allow liquid water to pool on their surfaces. The planets themselves range from 0.76 to 1.02 times Earth's radius, packed into orbits so tight that all 7 would fit inside Mercury's path around the Sun. Their host star is just 9% of the mass of our Sun, burning with a cool, steady dimness that stretches each year into a patient eternity. The discovery relied on transit photometry, a method that measures the slight dimming of starlight as each planet crosses the star's face. In TRAPPIST-1's case, the dips revealed not just the presence of planets, but their sizes, orbital periods, and even hints of their densities. The system's planets are locked in a delicate gravitational dance, with orbital resonances that keep them in step, each planet's year a simple ratio of its neighbors. This configuration hints at a gentle formation history, with planets migrating inward and settling into stable, tightly packed orbits. Because TRAPPIST-1 is so faint, its habitable zone lies close in, raising questions about tidal locking, where one side of each planet always faces the star. Scientists debate whether atmospheres could survive the star's flares, and whether liquid water could persist in the twilight bands between day and night. Yet the very existence of this system, 7 Earth-sized planets, 3 in the right zone for life, suggests that small, rocky worlds are not rare exceptions. With billions of similar stars scattered across the galaxy, the search for life has shifted from a long shot to a cosmic probability. In the 1980s, planetary scientists wondered if the crushing pressures deep inside Neptune and Uranus could do something outrageous, turn ordinary carbon into diamonds. At first, it sounded like pure fantasy, but calculations showed that, thousands of miles beneath those swirling clouds, carbon atoms might be squeezed so tightly that they would snap into diamond crystals and fall like rain. For decades, this idea hovered on the edge of science fiction, impossible to test on Earth, until a team at the SLAC National Accelerator Laboratory decided to try. In 2017, researchers at the LINAC Coherent Light Source set out to recreate the heart of a gas giant in the lab. They started with a sliver of plastic chosen because its atomic structure is similar to the methane found in Neptune's atmosphere. Then they blasted it with an ultra-powerful X-ray laser, generating shockwaves that ramped up the pressure to around 800 gigapascals, over 2 million times Earth's atmospheric pressure, and temperatures near 7,000 Kelvin. In less than a billionth of a second, the plastic vaporized, but in that instant, high-speed detectors picked up the formation of tiny diamond crystals, just a few nanometers wide. These nanodiamonds are minuscule compared to the gemstones we know, but the experiment proved the chemistry is real. If the same process unfolds on Neptune and Uranus, it would mean megaton layers of diamond raining down through the icy mantles, settling slowly toward the core. The idea of gemstone storms is no longer just a wild theory. It is a glimpse into the alien weather of our solar system's most mysterious worlds. And it all started with a flash of light in a California laboratory, showing that even the most exotic cosmic processes can be tested, one experiment at a time. April 2019. The world's astronomers gathered as a single image appeared on screens, a ring of fire, blurred at the edges, encircling a dark core. This was not an artist's impression or a simulation. For the first time, humanity had captured the shadow of a black hole. The subject was M87 Star, a supermassive black hole 55 million light-years away in the heart of the Virgo cluster. Its mass was 6.5 billion times the mass of the Sun. Its shadow was just 42 microarcseconds across, the width of a donut on the Moon seen from Earth. To make this image, scientists built a telescope the size of our planet. 8 observatories, from the Atacama Desert to the South Pole, linked together in perfect synchrony. This network, called the Event Horizon Telescope, used a technique known as very long baseline interferometry, timing radio waves arriving at each dish to a fraction of a trillionth of a second. Each observatory recorded petabytes of raw data onto hard drives, flown by plane and even sled from remote mountaintops and Antarctic ice. The real work began in darkened rooms, where teams spent months aligning, calibrating, and reconstructing signals using new algorithms designed for the task. The data was so vast, no internet connection on Earth could transfer it. Every byte had to arrive in person. The result was a glowing ring of superheated gas, light bending around the event horizon before plunging into darkness. At the center lies the shadow, the region where gravity is so strong, nothing, not even light, can escape. This matches Einstein's predictions for a black hole's photon ring, a final orbit for light itself. No telescope had ever seen this boundary before. The image confirmed a century of theory, turning the invisible into something real and measurable. For the first time, the edge of a black hole was revealed not through equations or inference, but through direct sight. What once seemed impossible, seeing the unseeable, became a photograph, forever changing our view of the universe. Across all 10 discoveries, a clear pattern emerges. The universe routinely breaks the boundaries of what we call impossible. Each breakthrough reveals that our laws of physics are just a starting point, not a limit. As new evidence overturns old certainties, science must adapt. The unknown is not shrinking, it is growing. Space keeps reminding us that reality is far stranger than we dare imagine. What discovery will rewrite the rules next?